Okay, Go has Go routines. What do we mean by a Go routine? A Go routine? It is a concurrent execution unit. Unlike threads, you can have a lot of them. They are very efficient, very lightweight, and it's very quick to switch back and forth between them. Anytime you make a function call, you have some function that you have declared. Okay, somewhere else in your code down here, you say y, and you call it. Anytime you make a function call for every function, including library functions, Go can choose to switch between different Go routines. And it contains, inside the runtime of the language, its own process scheduler. So you never know which Go routine you're running in. A Hello World program normally will have 4 to 10 Go routines running. When you do I/O, you do a printf. Your I/O is actually asynchronous from the program running. So you can actually print stuff, exit the program, and not see your output. Although that is difficult to do, it can be done. And we're going to see cases of that which are more common when we actually set things up to fail with concurrency. But how do you start a Go routine? What do you do to make one of these happen? Well, in the language, all you have to do, now if you just do y, it calls it, it runs it, it comes back to here. But suppose you say go y. This, instead of running it, the execution continues in the Go routine that you're running out here, immediately right there, and y now runs as an asynchronous sort of thread, lightweight thread, a Go routine. And you can do this a lot. Okay. The servers that I worked for down in Denver, we were running around 100,000 concurrent Go routines. I've done simulations on my laptop, and yes, I do have a fairly beefy Mac laptop where I've run 6 million Go routines on a laptop withoap difficulty. You can't run 6 million threads. You're lucky if you can run 2 threads in IBM WebSphere per physical CPU inside the machine. Okay? So, yeah, you can run these. It's trivial to start them. You will also see this kind of a syntax. Go func, and we'll say that this function has a parameter x that's an integer. And here's the body of the function. We'll just make it do something trivial, like time sleep. And we'll give it 4 times duration seconds. So it sleeps for 4 seconds. It then does a printout, fmt.printf. And we'll just have it print x\n. And that's the end of the Go routine. You notice the matching close squiggle for this one. And then here is the call. Put the parentheses right there. There's the function. It has no name. Okay, and we'll pass it 22. Okay, so, this is kind of a weird looking syntax, but it works and it's quick and you don't type much. And when you see a squiggle with parentheses around it, that means that, yes, you're doing a call right there. Now, this happens to be something kind of unique because this 22 is actually a closure on the value x, which means that if you pass stuff in, it's evaluated at this point in time and persists through the running of this function. Now, this function is in the context of a bigger piece of code here, and it has access like global variables to the scope outside. If you want to capture that scope at the time when the function starts, you can go in here and you can just declare a local variable and copy it into the local variables inside that function, which is also a closure. So you have concurrency and you have closures, things that are more associated with functional programming languages than they are with something that is compiled. In fact, I don't know of another compiled language, we're talking about compiled down to machine code, in existence that has these kind of features, especially the the feature of closures. And closures are incredibly useful. So this is a big feature. Now, as soon as we have concurrency, we ought to have some way of controlling that concurrency. And Go provides all the concurrency controls you can think of. And probably some you haven't thought of. So concurrency control suddenly becomes an important topic as soon as you allow concurrency. And you would think that other languages that have built-in concurrency would have good concurrency controls, like Node and JavaScript. Node.js implements JavaScript. It has asynchronous callbacks for all sorts of stuff, but it doesn't really have any concurrency controls. It does, but it doesn't. They're mostly implemented in libraries. They're not a part of the language itself, and they're done with yet more callbacks. And consequently, you can't read the code from top to bottom and make sense of it, because every time you have an asynchronous I/O, that runs at some point in the future. Which makes it annoying to debug. Whereas Go is a lot easier to understand and wrap your head around and actually get through it and understand what's going on. So in Go, there's a package called sync. We can import sync. And it has concurrency controls in it. It's not the only concurrency control, but it's the low-level stuff. And we can declare some sort of a variable. Name it a lock of type sync.mutex. And there are other kinds of locks. This one is just a simple lock-unlock. There are locks that are read-write locks that you can say, I want to get a read lock, I want to get a read lock, and a whole bunch of people can hold read locks, and then one of them wants to get a write lock, and it blocks everyone else from doing anything until that write lock is released. So we can say something like a lock.lock, and somewhere later in the code, a lock.unlock. Now, as soon as we have locks, we have the potential of, we did this piece, we locked it, but we never unlocked it. Okay. Go has a runtime that will detect this, and you will get an error, and it will say that you have a deadlock condition. It knows. There is also a tool, which if you're going to deal with locks and unlocks, you need to use this, which is a static checker for the language to determine if you have race conditions. So there are tools built around this that are very useful and very good. But the guarantee that if you lock something, that when you exit a particular routine where it was locked, that you unlock it, is you can do this. Instead of just doing that, you can say defer, okay, a lock, unlock, and on exit of the routine, wherever that is, even if you've got multiple returns in it, this unlock occurs. So there is a way to guarantee that even if something goes bad in the routine and you exited to do an error, you returned early, you still get this called use defer. Defer happens on exit of functions, and consequently, it isn't always what you wanted. Sometimes you're not going to want to defer. You're going to want to break this down and stick your unlocks at every location for various reasons. But that's kind of, the basic low level of locks and unlocks in this language. Now, built on top of locks and unlocks, there are other things. And we're going to come back to some of those other things, like waiting for a set of routines to complete. And the wonderful things we can do with that sort of stuff. A job scheduler is a trivial thing in Go. I mean, we're talking a couple hundred lines of code with Go routines and waits, and it's a trivial thing. It's just simple, okay? Something that would be mind-bogglingly difficult in other languages suddenly becomes easy. But with all of these concurrent things, we need a way of sending data back and forth. And there are these channels. Okay. And channels are communication points that you can send stuff into them, and you can get stuff back out of them. And they can be different sizes. And I'm not going to go into channels today. We are going to kind of spend some time looking at channels. But there are communication capabilities. And there's a way to say, and this is a huge one in terms of lots of language, that I've got a whole bunch of different communications coming into one point, and whichever one happens faster is the one that I want to run. So that you can do that effectively, that's built into the language. And that is one of those ones that, my goodness, the lack of that drives me absolutely bonkers, okay, in building front-end stuff. And yeah, I've got some front-end thing for my other class that I built, and I could not for the life of me figure out the concurrency stuff. And at some point in there, I went, you know what? We aren't going to try to figure it out. We're just going to put in a sleep and a repaint right here. And you see this all the time. I was looking at the code inside the New York Times front page, and suddenly I'm going, oh, look at that. They did the same trick. They've got a sleep and a repaint. Okay, because they have to have concurrency controls they don't have in JavaScript. And JavaScript is single-threaded. So, yeah. So, locks, concurrency, this is the stuff that makes it really important. Now, why would I want concurrency and locks in something when I'm going to access a blockchain? You know, I'd like to build my front end so it's responsive to the user, but at the same time, I've got to send this transaction off to Ethereum and it's not going to be done for 20 seconds, which means I need a way to be able to post transactions and run them concurrently and then get results back and then display it to the user. And that has to happen in my server code sometimes. So, yeah, that is the kind of a thing that you're looking at where suddenly these things, these communication and concurrency things, become super important in the language and really difficult to do in other languages like Java or C++ or Python.